Okay, so in this video I'm going to have a look at Theorem 19. And we're going to look at proving Theorem 19. And this basically says that the angle at the center of a circle standing on a given arc is twice the angle at any point of the circle standing on the same arc. In other words, if we take this circle here and we have this angle here, AOC, so this angle here is standing on this arc here, AC. So this angle here is standing on the arc AC. Now this angle here, ABC, this angle here is also standing on the arc AC, and this angle here is on the circle, or is at a point on the circle. This angle here will be twice this angle here. That's what we want to prove. Now, again, I'm going to use given to prove construction and proof. So we're given here a circle. So we're given a circle with center O, the center is O, and the arc, and we're given an arc AC. So this is the arc AC here. We're given a point B, which is on the circle, and we're given angles ABC, angles ABC and AOC. So we're given this angle here and this angle here. And we have this diagram here. Again, I've drawn it rough-hand. I'm not too good at drawing circles, but you need to use use a compass, draw it neatly, and use a ruler to draw these lines. So this is what we're given. So let's move on then to what we need to prove. So we need to prove. So what we need to prove then is that the angle AOC, this angle here, is twice this angle here. So that's twice the angle ABC. That's what we need to prove. This angle is twice this angle here. So next thing we're going to do is look at construction. And I've started the construction here. I've done the construction, in fact, earlier. Again, I've drawn a circle of sorts. Again, you need to do it neatly. I've done it freehand here. This is our original angle here, and this angle here. And we have our points A, B, and C, and our center O. Now, our construction just simply involves drawing a line straight down here from B to D through O. So we need to write that out. So our construction is join B to O and continue to D, to a point D. So then we just need to label all of these angles here. Label angles 1, 2, 3, 4, we have 5 and we have 6. Okay, so let's just move that up a little bit, and now we're just going to look at the proof itself. Okay, so the proof itself then just involves first of all we're going to look at OA so this is O here, remember, down to A. That's a radius of the circle, and that's going to be equal to OB, which is also a radius of the circle. So this radius here is obviously going to be the same as this radius here. And actually this is another radius here. We'll just look at these two first of all. This radius and this radius, they're the same. So they're both radii. And again, this is the reason for our statement. This is our statement here, and this is the reason for the statement. So these two here are radii, so they're both equal in length. Now, angle 1 must be equal to angle 2. This angle here must be the same as this angle here. Why? Because if this side and this side are equal in length, then this triangle here must be an isosceles triangle. So that angle must be equal to that angle there. So we would just write in here ISOSCELES, isosceles triangle. Right, so that means then that angle number 5 here, angle number 5, must be equal to angle 1 plus angle 2. So angle 5 must be equal to angle 1 and 2. Why is that? Well, this angle here must be equal to this angle and this angle. Well, from a previous theorem, this is an exterior angle, and from a previous theorem then we know that an exterior angle is equal to the sum of the two interior opposite angles. So we'll just write down exterior angle here. So this is an exterior angle equal to the sum of the two interior opposite angles. Okay, so that means if 1 and 2, if these two angles are the same, and angle 5 is equal to these two angles added, that would just simply mean then that angle 5 must be equal to twice angle 2. Because angle 1 is equal to angle 2. Angle 1 and 2 are the same angles, same size, because of it's in an isosceles triangle. So twice angle 2 would be just the same as angle 5. Okay, so from that then we can look at the other side as well and say that, well, angle 6 must be equal to twice angle 3. So angle 6 must be equal to twice angle 3. By the same reasoning, you've also got an isosceles triangle on this side, so angle 3 is equal to angle 4. Angle 6 is an exterior angle, so it's equal to angle 4 and angle 2 added. So angle 6 must be equal to twice angle 3, since 3 and 4 are equal. Okay, so let's just add these two then. We can say then that if we add angle 5 and angle 6, remember if we add angle 5 and angle 6, we get this angle here, which is one of the angles in our proof, in what we want to prove. So we can say angle 5 plus angle 6 must be equal to the two right hand sides equal. These two added must be equal to these two here added. So twice angle 2 plus twice angle 3. So angle 5 plus angle 6, angle 5 plus angle 6 must be equal to these two added. But now again we've got a 2 here and a 2 here, so we can factorize this. We can take 2 outside the bracket if you like. Angle 2 plus angle 3. So angle 5 plus angle 6 must be equal to twice angle 2 plus angle 3. But remember that angle 5 plus angle 6, angle 5 plus angle 6 is this angle here, which is the angle AOC. So the angle AOC, which is these two added, is equal to twice angle 2 plus angle 3. Angle 2 plus angle 3. Angle 2 plus angle 3 here is just angle ABC. Angle ABC. And this is exactly what we were asked to prove initially. If you go back to what we were asked to prove, angle AOC is equal to twice angle ABC. That's what we've ended up with here. So again, that's QE